Hi folks, welcome to this video on diagonal matrices and diagonalization. So we've got a lot to cover in this video actually, so I'm not going to dilly-dally. Let's start out with the definition for what it means to diagonalize a matrix. So we're going to start out with an n by n matrix D. Is diagonal if, well, I should say is a diagonal matrix. Let's do that. If Dij is equal to 0 for all I not equal to j. In other words, the only non-zero entries of a diagonal matrix are going to appear along the diagonal, hence the name. An n by n matrix A is diagonalizable if there exists an invertible matrix P so that A is equal to P D P inverse, where D is a diagonal matrix. Basically, all we're saying here is that A is going to be diagonalizable if it is similar to a diagonal matrix. Now, in our definition for similar matrices, we had P inverse B P, but P is the inverse of P inverse, so we can also express it in this manner. So from this, we get a nice little theorem. So let's look at that theorem. I'm going to not stop recording this time, and instead I'm going to just share my screen. There we go. And I'll make myself a little bigger here. Woo. All right, so theorem 22 is about diagonalizable matrices. Fun to say. So an n by n matrix is diagonalizable if and only if there exists an invertible matrix P with the columns x1, x2, x3 up to xn, where each of these xi's is an eigenvector of A. Additionally, if A is diagonalizable, the corresponding eigenvalues of A are the diagonal entries of the diagonal matrix D. So that's what theorem 22 is saying, in formal mathese, of course. So what is it saying in plain English? Well, what it's saying is the following. So let's say A has eigenvectors x1, x2, up to xn, let's say. And their corresponding eigenvalues are lambda 1, lambda 2, etc. Right? So those are our eigenvalues. Then what this is saying is we can diagonalize A by writing it as the matrix who has its columns of the eigenvectors. So I'll take that first eigenvector, that becomes the first column. Then I take the second eigenvector, that becomes the second column, and so on. Then this diagonal matrix that we have here is going to be lambda 1, lambda 2, all the way down to lambda n along the diagonal, and zeros elsewhere. And then we have this matrix's inverse. So if A is diagonalizable, this is how we can diagonalize it. And if we can't find an invertible matrix out of its eigenvectors, then it's not going to be diagonalizable. So that's actually going to be a thing that helps us out when we try to determine whether or not A is diagonalizable or not. So to help us see if a matrix is diagonalizable or not, first we're going to need to see, okay, does it have enough eigenvectors and enough different eigenvectors so that we get an invertible matrix? If we do, great, we can diagonalize. And if we don't, less great, we can't diagonalize. So let's do two examples. We're going to do one example where the matrix is not diagonalizable, so you can see what that's going to look like. And then we'll do an example where it is diagonalizable. All right, so for this first example, we're going to be looking at a 3x3 matrix A, and it just says diagonalize, if possible, this matrix here. And if we can diagonalize it, we want to state P and D, those matrices that are going to diagonalize it. And maybe I'll write that up here as a reminder. So if we are diagonalizable, then A is going to be P, D, P inverse. Okay, so in order to do this, based on that previous theorem, we have to find the eigenvalues and the eigenvectors of A. So I went ahead and did that beforehand. If you're taking your notes, there's a nice large space for you to write your notes there, because that is where you are going to find the eigenvalues and the eigenvectors of A as a check. Remember, we're towards the end of a semester, so there's probably going to be a final, and I'm probably going to want you to find eigenvalues and eigenvectors on that final. So make sure you're reviewing that at this point. So when I went through that work, I found eigenvalues the first one was 0, and it had multiplicity 1, meaning that this eigenvalue only occurred once. And then the second eigenvalue occurred twice, so it had multiplicity 2, and that was 3. When lambda 1 was 0, let's also state the eigenvectors. So when lambda was 0, I got an eigenvector of -1, 1, and 0. And when lambda was 2, I got an eigenvector of 1, -1, and 3. Now, I'll also just remind you about some stuff that we talked about with eigenvalues and eigenvectors, especially with regards to multiplicity. So we said that the multiplicity of an eigenvalue gives you kind of an upper bound on the dimension of the eigenspace for the eigenvalue. In other words, in this case, I said that lambda 2 had a multiplicity of 2, which really means that we have lambda 3 also equal to 3. So kind of like having a double root, right? So when that happens, you can get one eigenvector or two eigenvectors. So if your eigenvalue has a multiplicity of 5, you could have anywhere from 1 to 5 eigenvectors. In this particular case, we only ended up with one eigenvector. So in order to make sure, I'm kind of paralleling here that there are 3, I'm going to say that x3 is also equal to 1, -1, and 3. If I had gotten 2 different eigenvectors in this process, then x2 would be the first one and x3 would be the second one. So from this, if we are diagonalizable, then P would be formed out of these eigenvectors. So P would be the matrix 1, 1, 0, 1, -1, 3, 1, -1, 3. However, if you find the determinant of P, you're going to end up getting 0, which means that P inverse doesn't exist. So if I use these eigenvectors to create my hope at diagonalizing A, I got something that's not invertible. So since it's not invertible, we can't have this relationship, so we are not diagonalizable. So therefore, A is not diagonalizable. Diagonal. Hard to say, hard to spell, right? All right, so let's do another example. This time we'll look at a matrix that is diagonalizable so we can kind of see what that would look like or feel like. All righty, so as I was writing this example on the board, I realized that I remembered that I switched the order of these two examples in my notes, but I forgot to change their numbers. So we just did example 39, this is 38, but really this is 39 and that was 38. So sorry about the misnumbering, but it'll be fine. So in this example, we're going to diagonalize, if possible, this nice 2x2 matrix A. So we would go ahead and do the same thing. We're going to find the eigenvalues and eigenvectors for this matrix A. If you want to pause the video before I spoil the solution to that, you may do so and find those eigenvalues and eigenvectors for this 2x2. When I did the work, I got two eigenvalues. So I got an eigenvalue of lambda1 equaling 3 and lambda2 equaling -2. And I had corresponding eigenvectors. With 3, I got 3, 2. And with a -2, I got -1, 1. So these are my eigenvalues with their corresponding eigenvectors. So now we're going to see if we can form that matrix P when we were unable to do so before. So this time, if we have P, our matrix P, it's going to have each of these as its columns. So we have 3, 2, and -1, 1. So to see if this is invertible, we're going to find its determinant. So the determinant of P, oh, excuse me, is going to be 3 minus a -2, which is 5. So its determinant is not 0, which means we can find its inverse. So P inverse, I just said its determinant was 5, so it's going to be 1/5 times switch A and D, 1, 3, and negate the other 2. So let's check to make sure we can diagonalize this. What we said before is that the diagonal matrix we should get is going to have the eigenvectors along its diagonal. So we have 3 and then -2. So let's check to make sure that this is in fact correct. So is our matrix A 1, 2, 3, 0 indeed equal to P D P inverse? And I'm just going to leave that 1/5 factored out to make my life a little bit easier. So let's find these products. So if I multiply, I get 9. This was a 0. So we get 9. Then we're going to get 0 plus 2, 6, and -2. So I'm going to bring this coefficient of 1/5 out to the front. See, we get 9 minus 4, which is 5. And then 9 plus 6, which is 15. 6 plus 4 is 10. And then 6 minus 6 is 0. And when I multiply that by 1/5, I end up with 1, 2, 3, 0. Hooray! Cool. So when we diagonalized A, these were our matrices P, P inverse, and D that get things to be the way we would like them to be. So now that we know how to diagonalize a matrix, let's see why we might want to. So let's look at some properties of diagonal matrices or diagonalizable matrices. Alrighty, so we're going to look at a few theorems and talk about what those mean for our diagonalizable matrices, and then we'll do a few examples of exploring these theorems. So theorem 23 says, if A is an n by n matrix with m distinct eigenvalues with associated eigenvectors, then the collection of eigenvectors is linearly independent, which is kind of neat. So in other words, if you have your collection of all your eigenvectors for a particular matrix, then you're going to have linearly independent eigenvectors. What theorem 24 says is that if you have an n by n matrix with n distinct eigenvalues, then the matrix is diagonalizable. This kind of makes sense if we think back to that example that broke, right? Where we had one eigenvalue that had multiplicity 2, and we only got one eigenvector out of that. We could have gotten 2, but we only got 1. So what theorem 24 is saying, it says, I can't tell you anything about that particular example, but I can tell you if you have a 5 by 5 matrix and it has 5 different eigenvalues, it's diagonalizable. If you have a 5 by 5 matrix and it has 4 different eigenvalues, I can't help you, friends, sorry. Okay, so theorem 24 is helpful if we know, if we have the same number of eigenvectors as like our dimensions for a matrix. So this is leading into the question, if A is an n by n matrix with fewer than n distinct eigenvalues, can you conclude that it's not diagonalizable? And the answer is no, you can't. The reason being the particular example we happened to look at had an eigenvalue with multiplicity 2, and it ended up having just one eigenvector. However, you could have a matrix that has an eigenvalue with multiplicity 2 that has 2 eigenvectors. And in that case, because the values would be linearly independent, we would be good to go. Okay? So theorem 24 is strictly a one-directional theorem. It's not an if and only if. However, theorem 25 can help us figure out when it is diagonalizable. So if you have an n by n matrix, then it's going to be diagonalizable if and only if the dimension of the eigenspace for each eigenvalue is equal to the eigenvalue's multiplicity. In other words, if you have an eigenvalue, like we did in that example that broke, had a multiplicity 2, right? So if it had 2 eigenvectors, good to go. Fewer than 2, nope, then it's no longer diagonalizable. So if you have a 5 by 5 matrix, and let's say you have 2 eigenvalues with multiplicity 1, and then you have 1 eigenvalue with multiplicity 3. So that 5 by 5 matrix will be diagonalizable if that eigenvalue that had multiplicity of 3 has 3 eigenvectors associated to it that are different. If not, then it's not going to be diagonalizable. So all of this is going to help us when we go to find some different values. So in particular, we have a note about if I take a matrix and I raise it to a large power. Leonard, are you going to be all right with this? I don't know. I think he's expressing the concerns of the class. My word. It's going to be all right, babe. It's going to be okay. So note 10, it says the following. If D equal to Dij is a diagonal matrix, then D to the K power is equal to each of the Dij's raised to the K power. So in other words, if I have a diagonal matrix and I want to raise it to the 503rd power, those zeros are just going to stay 0 because then 0 to any power is 0. But the diagonals are now going to be raised to the 503rd power. So I can express the power of that matrix in that manner. So let's suppose that A is diagonalizable with this relationship. And all I did to get this relationship was I took our diagonalizable relationship, I multiplied by P inverse on the left, and I multiplied by P on the right. So that's how I ended up with P inverse A and then P on the right. Okay, so if A is diagonalizable, we could also express the relationship in this way. And we're going to write A to the K power in terms of P, D, and P inverse. So let's start that out. We've got A to the K. Well, A, okay, so since we're diagonalizable, we can come back to this relationship here. So we know that A is going to be P, D, P inverse to the Kth power. Now, unfortunately, we can't necessarily distribute this exponent here. And P is not diagonal necessarily. So we may have some messes going on in this, but let's just use what our definition of K power means. So if I'm being raised to the Kth power, it means take K copies of me and multiply me. So I'm going to kind of indicate that. So I'm going to take PD, P inverse, that's my first one. And then we'll take a second one, PD, P inverse. And then we'll take a third one, PD, P inverse, and so on. So we're going to do this K times. So we have a lot of matrices being multiplied here, which would be a real pain to do because matrix multiplication is not nice. But we do have some magic happening here. Hopefully you see it. So notice in this product, we have P inverse beside P. And we know that matrix multiplication is associative, so I can group these however I wish. And P inverse times P is the identity. And if I multiply by the identity matrix, nothing changes. So this product is going to cancel out, as will this one here, as will this one with the P that comes after it, as with this one with the P inverse that comes before it. So what happens is you get this really nice collapsing product. This P can't cancel, it stays in the front. And then I have D, 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 all the way up. So this is going to be D to the Kth power times P inverse. So what this means is if I want to raise my diagonalizable matrix A to the Kth power, I can. I'm still going to have to multiply by P and P inverse, but I have a diagonal matrix to the Kth power, which is easy enough for us to find. So let's do an example of finding a large power of a diagonalizable matrix and try this out. So for example 41, we are going to find this matrix to the 80th power. Now I picked this matrix so that we could kind of cut out a little bit of work because this is the matrix we saw from example 38. And that matrix was A. And we saw that we could diagonalize it by using this matrix for P, this one for P inverse, and then this matrix for D. So what this means is if we apply what we just saw in the previous example, this relationship here, we can find an expression for A to the 80th. So this is going to be 1, 2, 3, 0 to the 80th power. That's going to equal P, which is 3, 2, negative 1, 1, times D to the 80th, which is 3, 0, 0, negative 2, to the 80th power, times P inverse. And this time I will distribute that 1/5. So I get 1/5, negative 2/5. And then we have 1/5, 3/5. I feel like this is a Dr. Seuss book. 1/5, 2/5, 3/5, blue 5th. Okay, so yeah, so here's our expression that we would like to do. So what I'm going to do first is I'm going to simplify this expression in the middle. So since that's a diagonal matrix, we can find this matrix to the 80th power by raising each of these values to the 80th power. So 3 to the 80th It's just 3 to the 80th. Please do not multiply that out. Leave it as 3 to the 80th so we can keep our answers precise. Now this next one, we have a negative number, which is kind of interesting. So if you have negative 2 to the 80th power, that's going to give you a positive number. So we can rewrite this as 2 to the 80th. Be careful, because if we had an odd exponent, so if we had negative 2 to, say, the 81st power, that would be a negative 2 to the 81st. So when you're raising the diagonal entries to the exponent, just be mindful if you have a negative entry, whether the exponent is positive or negative, and how you're going to simplify that. So in this case, we're just going to get 2 to the 80th. And then we have 1/5 minus 2/5, 1/5, and 3/5. All right, so now we have to multiply, and we're going to end up with this like exponent in our product, but that's fine. So here I'm going to get 3 times 3 to the 80th. So that's going to be 3 to the 81st. Plus 0, so we get 0 there. Then here we have 0 minus 2 to the 80th. So we have a negative 2 to the 80th power. Here we're going to get a nice expression, 2 times 3 to the 80th, plus 0. And here we have 0, and then 2 to the 80th power. Times this beautiful fraction, 1/5, or matrix of fractions, 1/5, negative 2/5, 3/5. Okay. And then we're going to find this product in the same manner. And when I did that, I decided to factor the 1/5 out just to make my life a little easier. And here's the matrix I got. I had 3 to the 81st. Plus 2 to the 81st. Underneath that, I have 2 times 3 to the 80th. Minus 2 to the 81st. Then I have 3 to the 81st. Minus 3 times 2 to the 80th. And then I finished up with 2 times 3 to the 80th, plus 3 times 2 to the 80th. Okay, so let's just check my multiplication here for maybe this last coordinate so you can see where this came from. So I factored out the 5th, so I'm just going to be dealing with the numerators here. So to get this entry, I'm going to have to multiply the second row by the second column. So I'm going to get 2 times 3 to the 80th times 1. So this must be where my 2 times 3 to the 80th came from. Plus 2 to the 80th times 3. So that's my 2 to the 80th times 3. So this is going to be our result. So this matrix to the 80th power is this gorgeous matrix here. And as you can see, it probably would have been impossible to even come up with an expression as concise as this if we had multiplied this matrix by itself 80 times. That would be such a pain too, right? So that is going to be it for this video. Let's see what we'll be doing in our next video. Oh, so in our next video, we're going to be looking at eigenvalues that are not real. So we're going to be looking at complex and imaginary eigenvalues. And those turn out have a nice association with skew symmetric matrices and symmetric matrices. So that's what we'll be looking at in the next video. And then we'll just have one more video after that for the course. And then can you believe it? We'll be done. Semester seems so long and so short at the same time. So, so I hope you have a magnificent day, and I'll see you in the next one. Bye.